This module on three-phase separators describes separator types and components, principles of operation, and design procedures. Produced well fluids typically consist of varying amounts of oil, water, gas, and sediment. The first step in processing these fluids is to split them up into their individual components. This generally takes place at some type of separator. A three-phase separator uses gravity to separate produced well fluid into gas, oil, and water phases. Three-phase separators may be designed in either horizontal or vertical configurations. In a horizontal separator, fluid enters the vessel and hits an inlet diverter. The resulting sudden change in momentum provides the initial gross separation of liquid and vapor. The liquid collection section of the vessel must provide sufficient time for the oil and emulsion to form a layer or pad above the free water. A weir maintains the oil level, while an interface controller maintains the water level. The oil spills over the top of the weir, and then a level controller, which operates the oil dump valve, controls its level. An interface level controller senses the height of the oil-water interface. This controller signals the water dump valve to release as much water from the vessel as is needed to maintain the oil-water interface at design height. The gas flows horizontally and exits through a mist extractor to a pressure control valve, which maintains constant vessel pressure. In a vertical three-phase separator, flow enters the vessel through the side. As in the horizontal separator, the inlet diverter separates the bulk of the gas. A downcomer is used to transmit the liquid through the oil-gas interface to keep from disturbing the oil skimming action. A chimney equalizes gas pressure between the lower section and the gas section. The spreader, or downcomer outlet, is located at the oil-water interface. From this point, as the oil rises, any free water separates out from the oil phase. The water droplets flow counter-current to the oil. Similarly, the water flows downward, and oil droplets trapped in the water phase rise counter-current to the water flow. Selection of a separator type is based primarily on gas handling requirements and space availability. A horizontal separator is normally more efficient at handling large volumes of gas, and because of its large interfacial areas, it has better phase separation capability. It does not handle solids as well as a vertical separator, and it requires more space. A vertical separator, on the other hand, has good solids handling capability, requires far less space than a horizontal separator, and has much better liquid surge capacity, but it is more difficult to service. Regardless of type, all three-phase separators have in common certain internal vessel components. Inlet diverters provide the initial gross separation by changing the flow direction as fluid enters the vessel. The deflector baffle, shown here, is one type of commonly used inlet diverter. Another is the cyclone inlet. Wave breakers limit the wave propagation that might otherwise occur in large horizontal vessels. Defoaming plates reduce foaming at the gas-liquid interface, which tends to occur when gas bubbles are liberated from the liquid. A vortex breaker keeps vortexes from developing when the liquid control valve is open, thus preventing gas from being drawn out of the vapor space and re-entrained in the liquid outlet. Mist extractors coalesce and collect small liquid drops from separated gas before the gas leaves the vessel. Potential operating problems in three-phase separators include foaming crude, paraffin buildup, sand accumulation, liquid carryover, gas blow-by, and formation of emulsions. Separators must be sized properly in order to avoid such problems. Design procedures require a thorough understanding of the separator operating principles and their relation to such variables as settling of the oil droplets, retention time, and droplet size. The text that accompanies this presentation contains the necessary formulas for designing a three-phase separator, together with guidelines and step-by-step design procedures for sizing and selecting a separator. The text also has tables of maximum allowable working pressures for various vessel diameters, along with example exercises with solutions. After viewing this introductory video, please follow the sequence outlined here. First, read the process explanation. Then, review the equipment description. Then, study the design theory and procedure. Work through the design examples.